Okay, now we start with the various scheduling algorithms. What is a scheduling algorithm? Scheduling, as you know, is how you decide the sequence in which the various processes get executed. So a scheduling algorithm tells you which process to pick at each step. So what is the criterion based on which I'm going to pick one process from the bunch of processes which are sitting in the ready queue? That is what a scheduling algorithm tells me. So the first one we're going to look at is first come first served scheduling. So as the name suggests, it is the simplest scheduling algorithm, which says whichever process entered the ready queue first will be executed first, and so on. So this is the simplest use of the ready queue. So a queue, as you know, is a first in first out data structure. So by default a queue works like that. The process which entered first will be popped out first. So here we use the ready queue as a queue. We don't have any intricate logic or a very nuanced implementation or anything of that sort here. Whoever came first gets executed first, whoever came second is executed next, and so on. So so this again is an example of non-preemptive scheduling, because a process is taken and it is executed fully, then it terminates, and only then I pick my next process. There is no halting or no context switch which happens in between. So FCFS is non-preemptive scheduling. So we'll look at an example now. We'll take this case where we have three processes, P1, P2, P3, with burst times 24 units, 3 units and 3 units respectively. Burst time is the time required for that process to complete execution. So process P1 needs 24 CPU cycles or 24 units of time with a CPU in order to finish what it's supposed to do. Processes 2 and 3 need 3 units of time respectively. So when we do these scheduling algorithms, we draw something called a Gantt chart, which was a bar chart discovered or invented by this person called Gantt, which tells you where each process begins and ends and what is the sequence. So Gantt chart is basically this long horizontal bar where you fill in the process numbers and the time stamps. So here we have these three processes, P1, P2, P3, with burst times 24 units, 3 units and 3 units respectively. We're going to do first come first served, which means P1 is the first. So at time instance 0, we start P1, and for the next 24 time instances or time cycles or time units, we go on working on P1. Now at the 24th instance, P1 has been completed. So we go back to our queue and look at the next process, P2. So at 24, we pick up P2, which needs 3 time cycles or 3 units of time. So for the next 3 units, we work on P2. At 27, P2 has been completed. So we go to P3, we pick it up at 27, it needs 3 units of time. So for the next 3 units, we work on P3. At 30, P3 has been completed. We have no more processes to finish, so that is the end of our Gantt chart. So this is how these 3 processes would be executed in the order 1, 2, 3 if we were to use first come first served scheduling. So when we do scheduling, what we need to do is first construct the Gantt chart, then we need to compute the wait time and the turnaround time for each process. So if you remember in the previous segment, we looked at different scheduling criteria. We saw CPU utilization, we saw throughput, we saw response time, we saw a bunch of things. Generally, we look at wait time and turnaround time, both of which we are seeking to minimize. Now let's see for this example. Wait time, again I will remind you, because this is non-preemptive. Wait time is the time the process spends waiting in the ready queue, and because this is non-preemptive, it is only waiting until it has been picked up. Once it is picked up, there is no going back to the queue, no further waiting. So P1, the moment we started, we took up P1. So P1 has a waiting time of 0 milliseconds. P2, we took it up only at the 24th unit. So for P2, the waiting time is 24 milliseconds. Note that we assume all the processes have been in the queue right from time unit 0. There could be examples where they give you another column called arrival time, and there is a separate time instance for that as well, in which case your waiting time will be, it starts from the arrival instance and ends at wherever your process is put into the CPU. So we'll be looking at that in subsequent examples, so I will not confuse you with too much information right now. For time being, we assume all the processes entered at time interval 0. P1 was executed immediately, at least began execution immediately, so wait time is 0 milliseconds. P2 spent 24 milliseconds waiting for its term, and P3 spent 27 milliseconds. So the average waiting time is 0 plus 24 plus 27 whole divided by 3 is 17 milliseconds. Now we will also try to compute the turnaround time. Turnaround time, as we saw, is the time taken from the time the process enters your queue till the time it has been completed. So P1 entered the queue at time 0, it got completed at 24. So the turnaround time for P1 is 24 units. P2 entered the queue at 0 and it got completed at 27. So it is 27 units is the turnaround time for P2. For P3, it entered the queue at time 0, got completed at 30, so it is 30 milliseconds. Again, your average would be 24 plus 27 plus 30 whole divided by 3. You can do the math. So note that turnaround time is not the time gap from here to here. It is not how much space it occupies on the Gantt chart. It is from the time it enters the queue till the time it exits the Gantt chart. That is the turnaround time. So we have just finished scheduling using FCFS. We saw how to draw the Gantt chart. We saw how to compute the wait time and the turnaround time. Now the thing with FCFS, if you see, is these two are very small processes. But just because they came in later, they had to wait a whole lot of 24 seconds and 27 seconds respectively while this longer process was executing. If we had put these two first, both of these would have completed their execution in 6 seconds and then P1 could have taken the rest of the time. So what would have happened is the wait time would have significantly reduced. So we see that if we are looking at minimizing the wait time, then first come first served might not always be the most optimal scheduling algorithm to use, because if you have a very big process which comes first and then you have a bunch of smaller processes which come in a little later, then as long as the big process is executing, all these small processes have to keep waiting for that long duration of time. So your waiting time goes up. So that is a major disadvantage of your first come first served scheduling algorithm. So let us see in the upcoming segments if there is any alternative algorithm which overcomes this disadvantage.